Welcome to Chapter 2, in which the theory of acids and bases will be discussed. We start with Brønsted-Lowry acids and bases. Here, an acid is defined as a proton donor and a base is defined as a proton acceptor. A proton is a hydrogen atom without an electron. This table shows a couple of inorganic and organic acids and bases. Acids must have at least one proton and bases must have at least one lone electron pair. In 1923, Johannes Nicolaus Brønsted, who is a Danish chemist, and Thomas Martin Lowry, who is, or rather was, an English chemist, proposed this theory independently of each other. Therefore, the honor goes to both, and therefore we have this longer name. Many organic molecules have both basic and acidic sites, and these reactions will be very important in mechanistic chemistry. A Brønsted-Lowry acid-base reaction results always in the transfer of a proton from an acid to a base. That means we have conjugate acid-base pairs. The movement of electrons is shown with a curved arrow. That is a double-headed arrow because we move a lone pair consisting of two electrons. And acid-base reactions are always equilibrium reactions. The acid loses a proton to the base gains a proton from the acid, and on both sides of the equation you have either acid and base or conjugate acid and conjugate base. It is important that the pKa, or the negative decadic logarithm of the equilibrium constant of the proton dissociation in water, describes the strength of an acid. Of course, there are tables where we can see which acid has what pKa value. The equilibrium constant Ka is defined as the reaction products divided by the reaction starting materials, and if we multiply Ka with the concentration of water, which is 55.2 moles per liter, then we arrive at the acidity constant Ka, and the pKa is a negative decadic logarithm of Ka. And usually pKa values are found in the interval between -10 and +50. Here we see typical examples. HCl, as really strong acid, has a pKa of -7, and methane, as a really bad acid, has a pKa of 50. There is not enough methane in the solar system to see a single deprotonation event. In mixtures of acids and bases, the relative strength of acids and bases determines the outcome of the reaction, meaning where the equilibrium of the reaction can be found. In such cases we use an unequal equilibrium arrow indicated on which side the products are. Solving acid-base reaction equilibria can be done in 3 steps. First, we identify the acid and base in the starting materials. Second, we draw the products of proton transfer and identify the conjugate acid and base in the products, and then we look for the stronger acid. The pKa of the stronger acid is lower than the pKa of the weaker acid, because the pKa is a negative decadic logarithm of the equilibrium constant. Factors that determine acid strength are, of course, the elements of which the acids are composed, but then inductive effects, resonance effects, and hybridization effects. And we will discuss all four effects here. If we compare two acids, we always have to draw the structure of the conjugate bases, and then we have to determine which conjugate base is more stable, because if we have a more stable base, then the proton is given away much easier. Element effects are simple. Look at the electronegativity of various elements. If we have an element hydrogen bond, then the higher the electronegativity of the element is which is bonded to hydrogen, the stronger is the acid, meaning the smaller is the pKa. Then, looking at effects going down the column of a periodic table, we see that larger elements are better acids. So iodine is much larger than fluorine, therefore the electrostatic attraction between I-, which is large, and H+, which is small, is much weaker than between F-, which is small, and H+, which is small as well. Consequently, Hi is a much stronger acid. Inductive effects describe the pull of electron density through sigma bonds. Sigma bonds are single bonds, so they describe how the various electronegativities of elements forming a bond influences the electron distribution in a molecule, and again, element withdraw and push electron density through single bonds. Trifluoroethanol is a good example. The pKa of ethanol is 16 and of trifluoroethanol 12.4, so trifluoroethanol is the stronger acid because the fluorine atoms withdraw electron density from the first carbon, then that first carbon withdraws electron density from the second carbon, and that carbon does not give as freely as the carbon in ethanol to oxygen, which means the electron density at oxygen of trifluoroethanol is lower than of ethanol, and therefore trifluoroethanol is a better acid. Delocalization can cause dramatic changes. The pKa of ethanol is 16 and of acetic acid is 4.8. That's almost 12 orders of magnitudes in difference. And the reason for that is that the conjugate base of acetic acid is resonance delocalized, so technically we have only half of a charge on each oxygen, and therefore the recombination between H+ and O- is slower. If we plot the electrostatic potentials, then ethoxide has a concentrated negative charge, whereas acetate has a delocalized charge. Finally, let's look at hybridization effects. The pKa of ethane is 50, of ethylene 44, and of acetylene 25. Ethane is sp3 hybridized, only 25% S character. Ethylene is sp2 hybridized, 33% of S character, and acetylene is sp hybridized, so we have 50% S character, and as we see, S character is a quite determining factor. The last effect that we would like to discuss is the stability of conjugate bases. The higher the percentage of S character of the hybrid orbital, the more stable is the conjugate base, and therefore the stronger is the acid. In figure 2.5, the four factors that determine acid strengths are summarized. Again, element effects are governed by electronegativity, inductive effects by the withdrawal of electron density through single bonds, resonance effects and hybridization effects influence the stability of the conjugate base. This is a cooking procedure, how to determine the relative acidity of protons. We have to identify the atoms bonded to hydrogen because we would like to get a proton of the molecule, and if we have two hydrogen atoms in question that are bonded to the same element, then we have to draw the conjugate bases to find out which proton is released first. Typical questions are: do electron withdrawing groups stabilize the conjugate base? Is the conjugate base resonance better stabilized? Or how is the conjugate base hybridized? And usually we have to apply more than one of the rules, and we will have a couple of questions in Connect which deal with exactly these problems. Obviously, everybody knows acetic acid. Para-toluene sulfonic acid is a very commonly used acid that is soluble in organic solvents. If you look at bases, then sodium hydroxide, methoxide, ethoxide, and potassium tertiary butoxide are typical oxygen bases. Sodium amide and lithium diisopropylamide and sodium hydride are much stronger bases, but they are commonly used in organic synthesis. Strong bases have weak conjugate acids and vice versa. All strong bases are negatively charged, but not all groups that are negatively charged are strong bases. We have a couple of neutral bases like amines, which have a lone pair on their nitrogen. However, their negative relatives are stronger, and C- is also a rather strong base. However, please do not worry too much about strengths of acid and bases. If we use these concepts in organic mechanisms, I will provide you with the pKa values. We have not seen Gilbert Newton-Lewis for a while, so here I will present to you his concept of the electronic interaction of acid and bases. He also published that in 1923, the same year then Brønsted and Lowry published their theory independently of each other. So 1923 was really the year of acid and base theories. Please note, and that's important, that the Lewis concept of acid and bases has nothing in common with the concept of Brønsted and Lowry. Both concepts are existing independently of each other and must not be confused. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor, and Lewis acid and base reactions happen if an acid borrows a lone pair from a donor. Any species that is electron deficient and capable of accepting an electron pair is a Lewis acid, and any species which has an octet and at least one lone pair is a Lewis base. Here we see a typical example for a Lewis acid-base reaction. The lone pair of water reacts with the Lewis acid BF3, which has only an electron sextet, meaning it is 2 electrons short of its corresponding noble gas configuration. A Lewis acid is always an electrophile because it would like to have more electrons, and a Lewis base is always a nucleophile because it goes for Lewis acids. And importantly, Lewis acid-base reactions result very often in the formation of a new covalent bond. So when we have a carbocation, which is an electrophile, and a halide, here Br-, which is a nucleophile, then both can recombine to form a neutral molecule. Because aluminum is in the third column of the periodic table, it has only 3 outer electrons, and therefore if it binds to 3 chlorines, it still has only an electron sextet, and that makes it a Lewis acid. In a more complicated type of Lewis acid-base reaction, one bond is broken and another bond is formed. And to draw these reaction mechanisms, we have to identify the Lewis acids and bases first and then use curved arrows. For instance, in the alkene HCl reaction, we add HCl to a pi bond, so the pi bond reacts as Lewis base and the proton reacts as Lewis acid because it is 2 electrons short of the noble gas configuration of helium. So we have 2 electrons involved, and the double-headed arrow gets the proton and forms a new bond, and the chloride anion Cl- is left. On the carbon next to the carbon where the hydrogen has added, we leave a carbocation behind, which is another Lewis acid, which can then recombine with the Lewis base, the chloride anion, to a carbon chloride bond. We will practice this reaction mechanism many times. You will need Lewis and Brønsted theory of acids and bases for the reaction mechanisms to come. I'm not too fond of acid and base chemistry, however, the basics are really useful in learning organic mechanisms. So please make sure that you will be able to distinguish between Brønsted-Lowry and Lewis acid and base chemistry, because that will be one of the most important requirements for the chapters to come.